Hello everyone, I am a doctor in chemistry at the Research Center in Physico-Chemical Analysis. Today, I have the pleasure to present you my work which is entitled Molecular Docking Study of New Crystal Ligand Derived from 4-hydroxycoumarin with SARS-CoV-2 protein. In our work, we focused on theoretical study by molecular modeling to understand the mechanism of the SARS-CoV-2 MPRO protein by performing molecular docking calculations between SARS-CoV-2 MPRO and ligand L. The Covid19 pandemic is a new highly contagious infection caused by SARS-CoV-2, which has become a global public health challenge for which nation governments have imposed drastic measures to contain the pandemic. Major global efforts are underway to diagnose, treat, and prevent infection with the virus. Scientists around the world are uniting and working on a global scale to combat the coronavirus by developing new methods to reduce the disastrous consequences of Covid-19. In order to fight this disease, a new coumarin derivative, ligand L, has been synthesized and characterized within our team in few of its broad biological activities, such as antibacterial, antifungal, antioxidant, anti-inflammatory, anti-allergic, antiviral, hepatoprotective, anti-tumor, anticoagulant, anti-HIV, and anti-carcinogenic agents. To evaluate the mode of interaction of our ligand L with SARS-CoV-2 main protease, whose inhibition of this enzyme would prevent the virus from replication, a theoretical study by molecular modeling is performed. What is docking? Molecular modeling, and more precisely molecular docking, has repeatedly entered the field of biological research. It is defined as the search for the best pairing between two molecules. Why docking? The study of interactions is really simple experimentally, so simulations are used to observe how a molecule is placed with another molecule, to understand how the interaction takes place, which atoms interact, and predict on a series of molecules which one will present the best affinities. A docking simulation essentially consists of two complementary steps, docking and scoring. Docking consists in placing the ligand in the active site of protein and sampling the possible conformation, position, and orientation, retaining only those that represent the most favorable interaction modes. Scoring consists in evaluating the affinity between the ligand and the protein and giving a score to the position obtained during the docking phase. The molecular docking of SARS-CoV-2 MPRO-L binding mode was simulated using Autodoc tools Vino. This method allows explaining of the most energetically favorable binding sites of ligand L to SARS-CoV-2 MPRO receptor in terms of binding energy and inhibition constant. Through docking simulations, various parameters were obtained. The most essential parameters are the binding energy, which is equal to -7.03 kcal by mole, docking energy, which is equal to minus 8.3 kilocalories by mole, and inhibition constant, which is equal to 6.98 micromole, which show active AL molecule with the ability to inhibit SARS-CoV-2. Comparing the result found in this work with those reported in the literature, we found that both molecules, chloroquine and hydroxychloroquine, present low binding energy and a considerable values of inhibition constant. This high binding affinity is associated with the presence of multiple interactions with amino acids as shown in figure 1. In summary, the binding mode demonstrated in this study therefore provides a useful clue to understanding the possible molecular basis and interaction of this inhibitor AL with SARS-CoV-2. In conclusion, the interaction of ligand AL with SARS-CoV-2 improve revealed that the ligand AL binds to SARS-CoV-2 improve via multiple binding contacts. Through docking simulation, the binding energy calculated for SARS-CoV-2 improve AL complex and inhibition constant showed active AL molecule with the ability to inhibit SARS-CoV-2 COVID-19. Thank you for your attention.